So in the last class, we were looking at the lateral force generation. We said that the key factor in the lateral force generation was the distortion, which, of course, to the contact patch, which actually makes the tire assume a direction, okay, which is at an angle to the direction in which the tire is supposed to be moving. So if this is the straight running tire, and if you now, let's say that that is the central part, and then if you now give a steering input, okay, which we said is delta, and then actually there is a slip angle produced, and so on. And we saw that the distortion causes that centripetal force that's required in order to sustain the centripetal acceleration. In other words, cancels out the D'Alembert's force called the centrifugal force. The end of the class, we said that we get Fy, and then we have what is called as the restoring moment. Restoring moment is due to the centripetal force not actually acting at the center, and that it acts at a distance which we called as pneumatic trail, and then we had a curve which we plotted in the negative direction because it, okay, I think we plotted it together. Let me do the same thing here so that, yeah, that's what we get, and that is alpha. Remember that this is Fy, and remember that that is the mz, which is the self-aligning torque, right? This is what we did. So the question towards the end of the class, why I just brought this to your notice, is that why is this aligning torque? No, why is this taking this shape? Okay, in other words, why is the aligning torque becoming 0 when the force reaches that saturation point? Remember that the shear forces, okay, the shear force which is responsible for that Fy, okay, is something like this, right? So, and there's a moment also, there's a normal pressure which is, we'll just remove this, you know what is alpha now, so which is like that. Now, because of the fact that, assuming that there's no slip, because of the fact that it is now shifted to the left, in other words, there's an unsymmetric distribution, obviously the resultant force will not be symmetric, but is the resultant force, because of all those shears or all those pulls of those bristles which were there, they happen to be not symmetric, but it is unsymmetric, right? Now, imagine that slowly guys are not going to slip. When it slips, what happens? It reaches a maximum, okay, value which is mu into qz, right? So it sort of starts now pushing, because all of them are going to assume the value of mu qz, and this being almost symmetric, okay. This one, yes, it is not exactly symmetric, but it's assuming that it is almost symmetric. This guy is now going to move towards the center. So in other words, this situation where all of them have reached that mu qz, okay, which is the maximum force that can be delivered by these bristles, the resultant force position now shifts towards the center, and T goes to 0. So if you assume, for example, a good parabolic distribution, okay, the mu qz also will be parabolic, and hence it will be exactly symmetric, and the force sitting at the center Okay, so for a brush model with a parabolic pressure distribution, the aligning torque goes to 0. Right? Actually, it doesn't go exactly to 0 because the fact that it's not very symmetric, and hence it may actually be something like this, and so on. Okay. Now, the question we asked in the last class was that, is the lateral force development only due to cornering? Is there any other means of developing a lateral force? That brings us to a very important and interesting topic, which the tire manufacturers call as ply-steer and conicity. Ply-steer, as people call it, is something like a steer-like behavior, and conicity is something like a camber-like behavior. Now let's look at what is ply-steer. Yes, any questions? Okay. Now let's look at what is ply-steer. Let's say that that's the tire which is moving in this direction, rolling in that direction. Right? What's a tire? Let's look at this, say for example a truck tire. Similar is what you have for passenger car tires, and you have the tire here. Okay? Now it has what are called as belts. Okay? In this case, it is steel belts. Okay? And there are a number of belts. It can be 3 belts, 4 belts, and so on. Right? If you look at these belts closely, I'll just zoom that here and draw it here. If this is one belt, I already told you this, that there are steel cords which run like that, okay, which run like that, and that there may be another, there will be another belt, okay, which is where the steel cords run in different directions and so on. There's an angle to this. Let's not worry about that. What is exactly the angle and so on. Right. In other words, this whole of this belt bundle, the bundle which is just above what we call as the body ply, okay, behaves as a composite laminate. And what's the importance of composite laminate? It has a very interesting property. Maybe you've studied this in mechanics of materials. Okay, let's do that here. So if I have now a sheet, say for example made of steel, and then pull it, we told this already in last class that it just gets pulled, and that there is a Poisson's effect in the other direction. Okay. Now let's see what happens when I pull this here in this case. Now that's a sheet, okay, that consists of a number of all these what we call as reinforcements, these belts. Let's say that they're all together, and now I'm going to pull this sheet. Okay. If it were steel, I know what you would expect. It would just go like that, and this will be in one plane. There won't be out of plane, out of this plane. There won't be any deformations. All right? Now let's see what happens here. Yeah, you pull it. Oh wow, I didn't apply any force in the other direction. I just pulled it, and what happened? Whole thing twisted. Okay? So in other words, there's a coupling between this longitudinal force, or one force, to the other moment and so on. Right? Clear? So this is one running in one direction. If it were to run in another direction, then it would go the other way. Okay? So these are called as coupling stiffnesses. Okay? There is, in other words, a coupling happens between one plane, what happens in one plane, to another plane. In order to explain this, let's go into some details on the laminate theory. We will not go too much details into laminate theory, but we have to understand this. So we'll go into some details of the laminate theory. And what does this laminate theory say? Let's look at what we call as the constitutive relation for a laminate plate or laminated plate, or what is called as the laminate theory, right? So what are the forces and moments that act? See, what is the constitutive equation? I have in this case, forces, moment, and I have some terms here, constitutive terms, and this is what I would call as strains and so on, right? So let us say that I have nx force, ny, nxy, mx, my, mxy. Right? Okay. What is this? If I have a laminate like this, just give a small thickness to it so that the thickness is say 2h, and let's say that is the y direction and that's the x direction, and the force that is happening here is this nx, force here in this plane is, sorry, ny, force that's happening here or force that's pulling here is nx, and nxy is this, and nxy, nyx, and so on. Or in other words, if you want to write that as ny, okay, y, x is the plane, y is the direction. So if you want to write it like that, this becomes nyx, plane, direction, and nx. Right? Okay. We know that nxy should be equal and so on. Now, what's the right-hand side? The right-hand side of the strains, epsilon x, epsilon y, epsilon xy, and then it's a laminated plate, laminate theory, so you will have what we call as curvatures. So you have curvatures x, curvature y, xy. Right. Now, these two are related by these constitutive equations. Let's say that we'll divide it by 3 by 3, 3 by 3, 3 by 3, 3 by 3. So we'll call that as A, we'll call that as B, call that as B, and that we'll call it as D. Okay. Now, let's see what A is. So there are terms here. Let's not worry about how the terms are calculated. Any composite book will give you the terms, how it is calculated. So we will call that as A11, A12, 0, B11, B12, B16. Okay. So these are terms which depends upon the new values, EX, E values, and so on. Okay. So let's not worry what it is. That's not our intention. So you can go on like that, B12, B22, and A. So this is a way of, the numbers are important. So we'll write this as B26, okay, and this would be A. We'll say A12. Let's be, correct to a book. A22, 0, 0, 0, A66, B16, B26, B66, and that B gets repeated there again. Okay. Same way you will have D11, D12, and D. Yeah, they are values, okay, which are coefficients. What are they? Very similar to what you know, for example, in plane stress and plane strain. Okay. Say, for example, you have sigma is equal to E epsilon. right? So you have a constitutive equation, so which relates stress and strain. Okay, so this what do they depend? For example, in isotropic material, what enters into this E and nu. So you require two quantities for an isotropic material, E and nu. Okay, so here this is not this is a laminate, and so this is not an isotropic material. Okay, and hence you have a matrix which is similar to this. That's why I said let's not worry. Let's not go into the details. It's not to explain laminate theory, but to explain why it happens and how that causes what is called as the pleisthere. Yes.
So what is MXY?
MXY. Okay, good. So MX, MY, and MZ are the result of. They are the moments. Okay. Sigma x. Sigma, that is the sigma x multiplied by Z. Okay. dz minus h by 2 to plus h by 2. Similarly, my minus h by 2 to plus h by 2, sigma y into x into tz, right? And what is mxy? Sigma xy multiplied by z. So mxy is sorry. Okay, so the moments are the result of stresses that are acting in this plane. Remember we had a simple beam. Remember that we had a beam bending. That's the beam, say, for example, in your earlier classes on mechanics of materials. So when the beam bends, you would have, okay, how do you have this? So you have, for example, bends like this, okay, a moment that's created, and that would be the stresses that are acting, okay, sigma xx is a neutral axis, and that these stresses cause or equilibrate the moment. So that is what you get, right? Okay, it's exactly like that. It's a plate. What's a plate? You can assume that a beam is extruded in the other direction. So you have a plate, and the plate is extruded in the third direction. It becomes a beam extruded in the third direction. It becomes a plate. Okay, right. Any questions?
Notation changed from sigma to N over.
Yes. Yes. This is right. This is the way you express. I didn't say it's the same. I said it's similar. Okay. So this is the way you express for a laminated plate. Okay, so express it in terms of force, express it in terms of strains, as well as curvature. Right? Okay, and those forces are of course related to the stress through those kind of relationships.
Is NX the same as sigma x?
Exactly not the same. That is exactly what I'm trying to say. That that's the force that's acting. Nx is the force that's acting, and y.
In MX, is that sigma x or
Sigma x. When I define mx, I define it as sigma x or sigma xx if you want.
That
to
is not NX. The sigma.
No. That is sigma xx. Okay.
It is sigma xx into what into
Z. Z. Right? That's what creates the moment. Okay, you have nx, ny, and nz, right? That's the force that's acting in the x, y, and the z direction. Okay. Any questions? Right?
So the left hand side represents the stresses and the moments acting. The right hand side, the extreme matrix represents the deformations in X, Y.
Yeah. Please note nx is due to sigma x, which means that what is nx? How do you define nx? Just integrate minus h by 2 to from the same thing. If mx is like this, nx is that's it. Clear? Okay. So note the difference the way a plate is written and a regular constitutive equation. Can you call this as constitutive equation? Yes, you can keep debating that because constitutive equation is stress and strain for a material. Now you're talking about plate. Of course, agreed. Right? Any questions? So this is the equation which you would look at. Now, what do you mean by, okay, having understood that, what do we mean by coupling? What do you mean by coupling? When I apply epsilon x or epsilon xx, right? When I apply epsilon xx, I would expect a force nxx or nx. That's all I would expect. Okay. Now, there are, in the same fashion, x, epsilon y, and so on. Okay? But these coupling terms here give a different picture. So, for example, here I have B12, B22, B16, and so on. Right? What is the picture it gives? What is that you get from this? Okay, I give you a minute to understand that. So what is it that it gives?
Elongation also gives moment with force.
Correct. That's it. So, in other words, there is a coupling between the two in the sense that elongation also gives a moment. Okay, or shear gives a moment, okay, mx.
Vice versa?
Yeah, of course, because that's how it is populated, right? That's how it is populated. Isn't it? Right. So, in other words, if I change a curvature, term, say for example, kx term, if I change, then it is not that if I change this term, it is not that I get only a moment for changing the curvature. You would imagine that I have a plate like this, I change the curvature is changed only by giving a moment. This is what usually you think. But it not only does that happen, in other words, not only is the moment, of course, moment has an effect, but you would see that there are terms which would also give rise to your force. Clear? Okay. So, in other words, that's why what happened here is that when I stretched, twisted, and so on. Okay. How do I apply this? So, what is that we are talking about? Why are we talking about this? Changing curvature gives rise to a force. Fine. So, why? So, what happens? So, why is that I'm worried about it? Why is that I'm worried about it?
So if the tire, even though the vehicle moves in one direction, because there is deformation in one direction, there will be a reaction in all three directions as well as.
Suppose that's the belt. Okay, forget about direction, let's understand the physics. Suppose this is the belt, okay? Of course, you know that it is just circumferentially going. I'm looking at a cross section. Okay, that's the tire. That's the tire, and that's the belt. So when this tire hits the ground, or when it is sitting in the ground, in effect, what am I doing? I am changing the curvature. Okay? I am making this guy flat. Okay? In other words, I'm giving a moment to make it flat. When I give a moment to make it flat, okay, what am I attacking? I am attacking this. I'm attacking that. But when I attack that, or in other words, when I change kappa x, if I call that as kappa x, the curvature, if I change it, then there is one term which is sitting here, which I will multiply by kappa x in order to give nxy. Right? I change this, I give nxy term. It's a force term. Change this, here is one guy who's going to give me a force ny term, and so on. Right? So when I change kappa x, it is not just moment. So you would think that, fine, I have a curvature like that, I am making it flat. How do I make it flat? Maybe give a moment like that and make it flat. Right? But that's not just what happens. And you have forces. So in other words, I am producing a force here, right? And I'm producing a force this direction.
Sir, why are some terms of the A matrix 0?
Yeah, that's why I said that let's not. Why is that 0? Okay.
There is no coupling between those elements. Yeah.
Of course. Why?
That
Because there is no coupling term between the shear and the longitudinal force. Okay, Poisson's effect is only x to y direction. So gamma xy is g into, tau xy is equal to g into gamma xy. Okay, go back to your earlier class on mechanics of materials. All right? Okay, so there is, in other words, obviously, there is a shear term does not have any effect on the force term. Okay. Vice versa. Right? In other words, there is no coupling. What it simply means is that I would eliminate all these guys. These two guys will be done with, 0, no coupling, and I'll have only these two terms. These terms are your familiar terms. For a minute, forget about all this. So you would see that just force and, well known. Okay, A11 into epsilon x, A12 into epsilon y, 0 into epsilon xy or gamma xy, or however you call it. Okay, right? That's all. So the shear force is equal to, or the shear stress, which is the result here, is nothing but this multiplied by the shear strain. Right? Okay. Does that clarify your doubt that there is a shear term that's involved that has nothing to do with the normal force terms? Okay, let's come back. There's a lot more to look at it. So kappa x I'm going to change now because I'm going to make it flat. When I make it flat, obviously I'm introducing forces. Okay, I'm introducing forces because of this coupling term. And those forces introduce the lateral force, okay, the lateral force and a moment. And a moment. So simple fact that as the tire rolls on the ground and a part of the tire becomes flat results in a lateral force called plystère. Okay, so if I have this, these are the two tires which are running, and it's right. So this has a part of its belt flat, and hence there will be a force that will be acting.
So why can't we cancel that?
Yes, very good. So the question here is that does it get cancelled? It's a very important question. Can it get cancelled? See, let's say that I have this belt structure. Okay, now I have this belt structure. In other words, what happens if I rotate the tire, okay, if I rotate the tire and keep it? Okay. You have to be very careful in this. A lot of confusion for people in ply steer and that. Suppose I have this tire. Okay. How do I cancel it? If I have this force to act in the opposite direction, can I ever make it happen like that? Happen that way? Can you do that? You rotate it. You, whatever you want to do, you do. You rotate it. Okay, you rotate it, the structure will exactly be the same. Structure will exactly be the same. You rotate it like that, it will be like this. Put a point here, okay, that point will go here, this point will come here. So it's not, you can't cancel that. Okay? But if you rotate in the opposite direction, the force will be in the other direction. Okay? You can change that, in other words, by the structure of the ply in the two directions. So there is always a confusion that ply steer changes direction, whether you rotate it in clockwise or counterclockwise. True, but you don't rotate the tire, okay? You don't run the vehicle in the counterclockwise. You run it only in one direction. So you call this as the right tire, for example, and the left tire. Okay? And now superimpose on the, say, for example, I plot alpha versus both the aligning, this torque, which we called as aligning torque, a torque that happens, that's due to the nxy term, and a lateral force, the nx term. Okay, so that happens to be like this, and it so happens that because of the directions that you will get, if this is the lateral force, not left force, lateral force, if you want to call it like that, lateral force, okay, that is the aligning torque. And these are, in other words, when they are 0, not when alpha is equal to 0. In other words, when alpha is equal to 0, okay, what is alpha? Slip angle. We said slip angle alpha is required in order to produce a lateral force. So when it is 0, you would see that there is a lateral force and a corresponding moment. Clear? Hold this for a minute. We're going to come back to this graph. I'm going to explain it again. Is this clear? So when it's free rolling, okay, on a ground, nothing to do with the ground, you will get a lateral force. Okay. Now, there is also what is called as conicity. What is conicity? Name indicates that, conicity. As you had seen that there are what are called as belts. We saw that just now. Okay. So assume for a minute that the belts are not aligned exactly at the center. In other words, suppose I say that I cut this tire. Okay, let's forget this part of it. Okay, we will concentrate on only this part of the tire, top of the tire, right? That is where the belts are. The belts are supposed to be nicely placed. That is the center line. The belts are nicely placed like this. Okay, they are nicely placed with symmetric about the center. Right? I inflate it. There is a stiffness that's given. I inflate the tire. There's a stiffness that's given to the tire because of these belts. Okay, so it assumes a uniform, say, radius. or in other words, the deformations on either side is the same. Right? Let's say that that's the deformation due to inflation, okay, of the belt. Inflation with the presence of symmetric belts. Let's do a thought experiment. Let us say that the belts are not right symmetric about the center. They're not symmetric. They're not right. They're not symmetric about the center. They're not correctly placed. So I will have, say, let's say that there's a belt, what we call as belt offset. So this guy is like this. Okay? Left and the right placement of the belt are not symmetric. So what happens, what is that you conclude looking at this left hand side and the right hand side? What is that you conclude looking at the left hand side and the right hand side?
Radius on the left would be higher.
Fantastic. So radius in the left, when I inflate it, will be higher because this is going to be stiffer. So these guys sitting here, these material elements are not going to move to the same extent as to the left, and hence, okay, my tire is going to become something like that. In other words, my tire is going to look like a truncated cone. Right? So now you have a truncated cone. Let's say, let me just exaggerate that. And roll a cone. Roll a cone. What happens? So there will be a force generated. Yeah, bottom, yes, bottom surface will be flat, but still I am going to okay, like, it will be like this. There will be a conical shape. In other words, the pressure distributions on either side is not going to be the same. So with the result, there's a cone, it's as if there's a cone sitting and then rolling.
At any time when the wheel and tire interacts with the road, the surface is always flat, right?
The surface, correct, agree with you. Surface is flat, but the pressure distributions are not going to be the same. Okay, that's exactly what happens in a cone. The cone is also, when it's placed, okay, it assumes the surface, and one side becomes flat. It's not that it is like this. It becomes flat. So when you rotate it, why is that it's not going straight? It goes like this, right? Yeah. Exactly the same thing. Right? Okay. So the cone, you are placing it on the ground, which means that, please note that one side of the cone is sitting like this. So the cone will be sitting like this. Okay? Fine. So this is what is called as the conicity effect. That's giving rise to a force. Right. Now, this is one thing which is not necessarily is one side or the other side, because it depends upon which side it is shifted. So if you now take a number of tires, you go to one of the manufacturing plants, tire manufacturing plants, you take hundreds of tires. Now, and then, okay, say that I measure hundreds of tires, I measure the lateral force. Let's say that is the lateral force. Let's say that's positive, and that is negative. And let's say that this is the number of tires. I take 1,000 tires. What would happen is that, okay, you will get, suppose I get a peak like this, a very pointed peak, okay, and say I get a peak, or I get something like this. Okay? Right. I have tires which are, so if I get a peak like this, suppose I get a peak like this in the tires, if I get a peak like that in the tires which I've tested, which this means, 1 minute, this means that this peak is what? All the tires, whatever I've tested, okay, this is falls, say, let us say that it falls within this gap. All the tires which falls within this gap, small gap, almost the same, then that lateral force is pleisteic, because pleisteic is due to the design. Okay? Here, if it so happens that the force distribution is something like that, then that's not pleisteic. That's not pleisteic, basically because it is distributed on either side, and so the belts are offset this side or offset the other side. Right. Okay, we'll come to the effect, this diagram in a minute. Let's go and look at, are there any other things that cause a peculiar behavior of the tire? Right? So in other words, straight running tire, is it going to be a nice guy who's going to run straight, or he's going to do other magic, other things? Yes.
Is the Conicity a manufacturing defect, or is it something else?
Yes, it is. In most instances, it is this belt offset that's going to cause conicity. Okay, it's a defect. Right. Now that's not the end of the story. There are other things that are happening which are peculiar and which is not covered by all your courses in mechanics of materials. Now, what are the other things that are happening? Okay, let's look at that now. Now, let's look at the contact pressure distribution, okay, and the lateral forces that take place, or that's present when I roll the tire. Okay? Now, you see two things there. So that's the lateral force distribution. Right? There's a lateral force distribution that's happening. What is the importance of this lateral force distribution? Okay? Now, why is this important, and what is that we are going to look at? Actually, that's the previous picture is just to zoom in and show you the values, the inner ones. Okay. Now, that is in the longitudinal direction. In order to understand that, picture, we'll come back again to the lateral force and longitudinal force. Now, let us assume that the tread is a block. Okay? Now, if you looked at these blocks, they are not straight, squares like this. That's a plan view. This is a plan view, and so they're not nice squares like this. Okay, they are a rhombus type of figures. Okay, all those blocks are rhombus type of figures. Right? We will explain this in a minute. We will come back to that. So, in other words, they are not what is there at the top. Okay, they are more a rhombus type of figures. Right. Now, what happens when I apply? See, let us say that, let's now model this blocks. This is a plan view. Okay. So now let me model this block, okay, and apply a force, say a square block, apply a force in this direction. I'm applying a force in this direction, okay, for both these things. Right. Now let's see what happens. Okay. So I can do two things. One is that both of them, the bottom and the top, are fixed not to move in the Z direction. Okay. Okay, both of them are, the guy is stuck between two platens. This is what happens to a block when it is in the middle of the contact patch. At the edges of the contact patch, one guy is free. Okay, so I can free him. Okay, we'll apply this load. Let's say that I have a square cross section. I apply this load. Okay, what do you expect? You expect it to move the direction or bend in the direction in which I am applying the force F for a square block. I change this block to rhombus. You would see that there's a difference. Okay? Now, that's the top view. That's the top view. See what has happened. Of course, it's out. See what has happened. Let's concentrate on the left side. So, the left side clearly shows that this is a finite element picture. It's just a isotropic rubber block. So, it shows that when I apply a force F, the displacement Fx, let me call that as Fx, the displacement is only in the x direction. For that rhombus, okay, which is very similar to that there in the block, in the tread block, if I apply a force Fx, that is Fx, there is also a displacement. Look at that. There is a displacement in the other direction, y. You can see that at the bottom picture. Civil engineers long ago recognized this and called this as unsymmetric bending. In fact, when you take this next course on automotive structures, we're going to talk a lot about unsymmetric bending. Okay, they realized that there is a principal axis directions, okay, along which there is no coupling. And again, there's a coupling factor that is involved because I am not applying the force along the principal axis direction, which happens to be the symmetric axes, okay, that you see, for example, in the first picture. So if I now have a block whose plan is like that, and if I have symmetric axes, okay, it is symmetric bendings. It's a simple cantilever beam that bends. But of course, it's not a cantilever beam as you know or you have studied it because it is a short, fat fellow. Okay, hence shear deformations become very important. There are other things that are happening. And a simple beam theory, which you have learned, a cantilever beam theory cannot be applied. Okay, that's one thing. Now, if this plan view happens to be not so symmetric, say now it is something like this, and I'm applying a load here in that direction, that's not a symmetric axis, and hence a coupling happens in the other direction, okay, and hence there is a push. Okay, now that, in other words, that results in, if I stop it, that results in a force. If I stop this, that results in a force. Okay, so if now go back to my first picture, we'll explain that in the next class again. Now I have shears that are happening. Okay, let us say that I have these kind of rhombus blocks sitting like this, okay, and there are going to be, even if when it's rolling, remember that there are going to be lateral shear forces that are going to happen, okay. That would be the lateral shear forces that would happen or that would act on these threads, and that lateral shear forces results in forces that are acting in that direction, okay, and hence would result in a torque which is called as the Pratt, P-R-A-T, Pleisteier residual aligning torque. I have to be careful in this, but anyway, that shape is, there will be, this is a very simple method, simple thing, but there will be because of this shear forces that are acting, okay, as it goes straight, there are shear forces that are acting, okay. Remember that the way the contact pressure shear distribution was there. So because of these shear forces that are acting, there are forces, because of this coupling, there are forces perpendicular to those shear forces, okay. At the ends, there are shear forces like that, and this is the shoulder region where there are shear forces which are happening like this, and at the end of the contact patch you have shear forces that are happening like that, and because of which, okay, you have coupled forces which come along with these shear forces, and the coupled forces which are acting perpendicular to these shear forces. So if there's a shear force like this, that's the contact patch, say that's the end of the contact patch, and so the contact patch you have, okay, shear happening like this, here it's happening like this, and these two, they're happening like that. And so there is always a perpendicular force that's happening, okay, that's the result of this coupling. So when you have perpendicular forces that are present, and that results in a torque, okay, towards the center of the tire, this is the center of the tire, okay. In other words, you see that that's the So that's the center of the tire, and so there is a moment that's acting. So this is another reason why there's an aligning torque that's happening when you're going straight. Okay, we'll come back to this, and we'll continue with this and the other derivations in the next class.